That's all. Okay. So today we'll start from the our next important component, that is nothing but capacitors. So the objective of this session is what is the capacitor types, how to identify the capacitance of capacitor in the various materials used, and voltage handling capacity of the capacitor, then series parallel equivalents and various applications. So first of all, what is that capacitor? It is basically used to block the DC and pass AC signal, and hence can say either to store the energy or can be used as a filter, right? So you all people are familiar with this sentence. Capacitor blocks the DC and passes AC, is it? So why? That also we will discuss in the next slide. Then the capacitors are available again basically in 2 to 3 types. That is like fixed polarized capacitor, that means having the polarity. Generally we are calling it as a electrolytic capacitor, and mostly it is preferred to store the energy like in voltage multipliers, rectifiers, power supplies, etc. Okay, and another one in that fixed type, that is non-polarized, that means don't have the polarity. And under that non-polarized, basically the available capacitors, which we know, that is ceramic, then polyester paper, mica type, etc. Again, these capacitors are used as a filter. You might have studied about low pass filter, high pass filter, band pass filter, all pass filter, etc. during your previous year syllabus, integrated circuit. I think last unit was there, that is op-amp based filters. And next one is variable non-polarized. Variable non-polarized means again same as that of whatever resistors we discussed up to our previous lecture, like variable resistor potentiometers, same as that of resistors. Capacitors are also available as a variable one. And the best example, if uh, you have seen the old radios, then to tune that radio to a particular station, we have to change the capacitance of that tune amplifier which is available inside that radio. Okay. Today also you are using, but that is not, we can say, actual or physically we are changing that capacitance. See, in our mobile handset, whenever you are tuning to a particular FM, like Radio Mirchi 98.3 or that 95 point something, 93.5 is there. Am I right? 104 point something, right now. So all these are the FMs, and if we do not tune to that particular number, that frequency which is available in megahertz, for example 98.3 megahertz, that we have to tune it properly, then and then we are getting uh, that signal properly, that means without any noise, right? So such type of capacitors, that is variable capacitors, are used for the tuning purpose. They are basically known as a trimmer also, or in all that radios, whatever variable capacitors are going to be used are known as a GaN capacitors. You might have heard this word in your analog communication. Okay, that GaN capacitor is nothing but the variable capacitor. It is used basically to set the required capacitance in the circuit. That is, here I given the example already, that is tune amplifiers and in radio receivers. Now, the how to identify the capacitance of that capacitor. So remember, either that capacitance it is directly mentioned on that capacitor, or some, we can say, universal code is written on that. By that code, we can identify it, or same as that of various color band resistors. Capacitors are also available with color bands. You might not have seen such type of capacitors. That also we discuss in the next slide. Okay. So first one, to which you are mostly familiar, that is ceramic type capacitor. You might have seen it in our lab also. So the number is given, a particular number is written on that capacitor, and by that number we have to identify its capacitance. So here I taken one example. The ceramic type of capacitor is shown with the number as 2 to 4. Okay. So how to identify the capacitance of that capacitor? So first of all, note down first two digits as it is, that is 22 into that 10 is again compulsory, and its power, that is the third number, and that picofarad it is also compulsory, remember. Okay, so 22 into 10 raised to 4 picofarad is compulsory. So whenever you will adjust that digits 10 raised to powers, you will have that answer as 22 into 10 raised to minus 8 farad. Okay, pico means minus 12. Okay, and hence when you will just rearrange it, so you will have that value as a standard one as 220 nanofarad. Nanofarad means 10 raised to minus 9. Okay, so this is the type of ceramic capacitor, and how to identify the capacitance of that ceramic capacitor. These capacitors are basically used for the filtration purpose, or to remove the noise, or in our electronic filters, such as low pass filter, high pass filter, band pass, band reject, all pass, etc., etc. Second order, higher order, etc. Then the another type of capacitor, again you might have seen it in our lab only, that is electrolytic capacitor. It is a polarized capacitor. That means this capacitor have the polarity. By mistake, suppose we have connected this capacitor with opposite polarity in the circuit, there may be a chance of damage of that capacitor. It gets burst due to the reverse charging of this capacitor. So the care you have to take while using this electrolytic capacitor with its polarity. Now remember how to identify the positive and negative terminals. See, in this image, you will observe one white side over here and somewhat just like a negative sign printed on it, right? So the terminal which is closer to that negative sign shown is nothing but negative terminal simply, and opposite one will be by default positive. Another way is also there with their length of that terminal. The terminal having more length is the positive terminal, and remaining one will be by default again negative. But this is not the we can say standard method to find out the positive and negative terminal, because you people, suppose somebody just cut down this long terminal and then it's short as compared to that negative one, and if you try to identify the terminals of that potentiometer by their length, then 101% you will be able to connect that capacitor with opposite polarity, and there will be a chance of damage. So instead of that, just it is already written, printed on that capacitor which terminal is negative, so try to prefer that. Okay. Now, as it is a electrolytic type of capacitor, that means polarized capacitor, this capacitor will have the voltage handling capacity, or in another word, we can say the voltage storing capacity. You will observe the number is written as a 200 V. That means the shown capacitor, electrolytic capacitor, can store the DC voltage up to 200 volts. Beyond that, if we try to charge it, it will get burst. And another number is also given, that is its capacitance. It is directly written on the capacitor. It is written as 470 microfarad. So this capacitor, as it is electrolytic type or polarized capacitor, we can say it is of 470 microfarad. That is its capacitance, and voltage handling capacity, or that voltage storing capacity, as 200 volts. Okay. Now the next one, that is polyester type, and basically these capacitors are available with somewhat color code. You might not have seen such type of capacitor. I think these capacitors are not available in our lab also. Is it? Are you getting?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, in such type of capacitors, how to identify the its capacitance as well as voltage handling capacity of that capacitor, as well as the tolerance is also available. Okay. So I taken one example. See that color chart. It is almost same as that of the color chart used. That means the numbering sequence or the number assigned to particular colors. It is same as that of whatever we discussed for registers. So the sequence is also same, that is black, brown, red, orange, yellow, green, blue, violet, gray, and last one is white. And numbers are assigned starting from 0 to 9. Okay. Now the tolerance, the only two type of tolerance bands are available, that is either green or white. If the tolerance band is of green color, then it is of 5%. That means the capacitance of that capacitor may get vary by plus minus 5%. Similarly, for white band, it is of plus minus 10%. Again, one more different thing is given with this type of device, that is its voltage reading by the color code. Again, you will observe only two types of colors are mentioned, that is for voltage rating. Means here we can say these capacitors are available only with two voltage handling capacity ratings, that is either 250 volt or 400 volt. If it is available with 250 volts voltage handling capacity or as a voltage rating, then that color band will be of red color, and for yellow it will be of 400 volts as per this shown table. Right. Now how to identify? Opposite to that of terminals. Start from here. This is the opposite end of that capacitor. That means we can say opposite to the external connecting terminals. You just start to note down that colors. So for this first one, that is red. So for red, the number assigned is 2 already by this table. You can check it. So I written 2 as it is. Then the second band, that is violet, it is of 7. So I written it directly as 27. Here I do not prefer that 10, but you can prefer it because the same methodology we use for identification of resistor as well as the ceramic type of capacitor. Just we discuss it, right? So 27 into, you can write that 10 as a compulsory, and third color band, and its assigned number, that is, here it is yellow. For yellow it is 4, so 10 raised to 4. And picofarad, you have to write it compulsory. Same as that of previously discussed ceramic type of capacitor. So that picofarad is compulsory, you have to write. So 27 into 10 raised to 4. Are you getting that third color band? That is the power of 10. Its assigned number, that is the power of 10. Here the third color band is of yellow color and the assigned number is 4. That's why you have to write it as 27 into 10 raised to 4, and picofarad is compulsory. So again, when you will recalculate or you will adjust the digits, you will identify this capacitor is of 270 nanofarad. Okay. Now the fourth color band, that is of green color, right? So that fourth color band is for tolerance purpose. Remember the difference. In case of resistor, the last band was for tolerance. Here the second last band is for tolerance. This difference you have to remember. So this fourth color band, here it is shown as a green color. That means this capacitor will have the tolerance of 5%, right? And the last color band, that is the remaining part of that capacitor, that, or the, we can say, remaining body of that capacitor, it is colored by yellow color, is it? And that last one here, the largely shown part of that color, that is for its voltage rating or voltage handling capacity. As it is yellow color, for yellow color, that voltage handling rating is 400 volts. So how you will write the details of this capacitor? This capacitor having the capacitance of 270 nanofarad with its tolerance as a 5% and voltage handling capacity as 400 volts. Is it clear?
Yes.
Those who are hearing me, is it clear? Any doubt?
Yes,
Yes,
sir.
sir.
Yes,
No.
sir.
No.
So I think you might not have seen such type of capacitor, right now. Now the next one, again that example is taken, that is red, then orange. Okay, so how you will identify its capacitance? Red means that numbers will be 2 into, for orange, that is the, its assigned number, that is the power of 10. So 22 into 10 raised to the number assigned to Rn, that is 3. And picofarad is again compulsory. So this capacitor will be of 22 nanofarad. Then the fourth color band, that is for tolerance, again it is green. That means the tolerance will be of 5%. And the voltage rating, it is of red color, this much power. Right. So for red color, already I told it is given in this table as a 250 volts. So how you will read the details of this capacitor now? This capacitor have the capacitance of 22 nanofarad with its tolerance as 5% and the voltage handling capacity as a 250 volts. And the last example, the first color band, that is for orange, second one is white. So to identify the capacitance of capacitor, what we are doing, we are taking first two assigned numbers for that colors as it is, that is 3 and 9. So I written here 39 into 10 raised to the number assigned to that third color band. Here that third color band is red color. So 10 raised to 2. Okay. And again picofarad as it is. So this capacitor is of 3.9 nanofarad, 3.9 nanofarad, and the fourth band, that is for tolerance. Now the tolerance band is white, that means it has that tolerance of 10%. So I written the same 10%, and the last one again, that is for voltage rating. Again it is yellow color, that means of 400 volts. So this capacitor is of 3.9 nanofarad with plus minus 10% tolerance and voltage handling capacity as 400 volts. Okay. Now we will see about the one important term with this, with all these capacitors, that is nothing but the resistance offered by that capacitor whenever we are using it in our applications or in our various electronic circuits. A simple diagram I shown purposely here. The input is shown as a AC signal. In that input signal source, in series, a capacitor is connected and the output is taken out across this resistive load RL. Right. So see, the resistance offered by this capacitor, to which it is not actually the resistance, because whenever we are saying resistance, the resistance is independent of signal frequency as well as we can say amplitude. Am I right? Whenever we studied resistor, we never consider which type of signal is applied to that resistor. That means either AC signal is applied or DC signal is applied. So that resistor will be on to provide the same resistance. That resistance will not going on to change. It is a fix. But in case of capacitor, whatever resistance that capacitor will go on to provide, it is totally dependent on what we are applying as an input to it. So as per this first diagram, here I shown the input as a AC, the resistance which we are calling as a reactance of that capacitor, it is denoted by Xc, which is equals to 1 upon 2 pi Fc. You are well familiar with this formula, I know it. In this formula, what is that F? It is the frequency of that applied input signal, and C, it is the capacitance of that capacitor. So whatever reactance that capacitor will be going to offer, that reactance will be dependent on, in this case, the F in, that means the input signal frequency. And that's why I replace in the next diagram that capacitor just looking like a variable resistor, right? That variable resistor offers somewhat its resistance, that is Xc, that is dependent on 1 upon 2 pi Fc, or that Xc can be determined as 1 by 2 pi Fc. Here, the F is nothing but, already I told, that is the input signal frequency, right? So see, if instead of this time varying signal or AC signal, if I replace it by DC voltage source, just imagine a DC voltage source is there as an input signal, what output you will get? Our VO will be equals to how much? Just think about it.
0.
VO will be 0. Correct, 100% correct. Because see, whenever DC signal you will apply it as an input, for that DC signal, the reactance offered by capacitor will be equals to Xc equals to 1 upon 2 pi Fc, where F is the frequency. And as the input signal, we are considering it as a DC signal, that means F will be 0. and 1 by 0, that is nothing but infinite. Am I right? So for DC signal, this capacitor will go on to provide the infinite reactance. Now, what is mean by infinite reactance? Here we can say there will be no physical contact between two terminals of that capacitor. That two terminals will act as open circuited from each other. That is nothing but infinite reactance. Yes or no? Nothing is there between two terminals. That means whenever signal enters from one terminal and goes out from the second terminal, whatever resistance inside that capacitor between that two terminals will be going to offer, that will be dependent on input signal frequency. Now here input signal frequency, we are considering it as a 0 hertz, and that's why the resistance, or we can say reactance, offered by that capacitor, that will be equals to infinite. Now infinite reactance means that two terminals will act as completely open circuited from each other. That means this capacitor will be going to act as an open switch if this Vin is equals to DC. Our input signal source is DC source, right? And whenever it will going to act as an open switch, no current going on to flow from source through capacitor through the load, and that's why how much will be the VO? That is nothing but drop across RL, as I will be equals to 0 through RL, drop will be 0, and that's why VO will be equals to 0. If I applied a very small frequency signal as a VIN, sinusoidal signal, but a very low frequency, then what will happen with this VO? That VO will be non-zero, but it will be very, very small. Are you agree with this? See, second condition. Are you got the first condition? If I applied input as a DC voltage source, how much will be the output voltage? Output voltage will be 0, because that capacitor will be going to offer the infinite reactance. That means it will act as an open switch. That means the current flowing through that capacitor will be 0, and hence we can say current flowing through load resistance, that is RL, will be 0, and as I will be 0, the drop across RL, that is nothing but VO, it will be equals to 0. Is it clear? अरे सगळ्यांना समजतंय का?
Yes sir.
Yes sir, yes.
मी नुसतीच बडबड करतोय हा. मला दिसत नाहीये, मी स्क्रीन शेअरिंग केली आहे. मला माहित नाही बॅक एंडला काय चालू आहे. तुम्ही चॅट बॉक्स मध्ये काही टाकत असाल, आय डोंट नो इट, कारण मी ते रीड नाही करू शकत आहे. ओके, फक्त मला रिॲक्ट करत जा मी विचारल्यानंतर. राईट. So second condition we will take, that is Vin as a time varying signal, or we can say sinusoidal signal, but its frequency is very, very low, just above 0 hertz. For example, here we'll take the example just like a 10 hertz. So this input signal will consider as a 10 volt peak to peak with 10 hertz sine wave. Imagine करतायत ना सगळे? Second condition we
Yes,
taken, that input signal as a sine wave with 10 volt peak to peak with frequency just 10 hertz. Right? So for this 10 hertz, the reactance offered by this capacitor, it will not be equals to infinite now. If this capacitor is of, we can say 0.1 microfarad. Okay. So yeah, for proper understanding purpose, you just take notebook and pen and and try to calculate it. See, Vin we are considering as 10 volts peak to peak with 10 hertz frequency, and the capacitor connected in this circuit, if it is of, we can say 0.1 microfarad. Load resistance is 1 kilo ohm. Then Vin
So capacitor value
0.1 microfarad. 0.1 micro. That means 0.1 into 10 raised to minus 6. Okay. Now, if such type of signal is applied as an input to the shown circuit means it is resistive capacitive circuit, we can easily find out the output voltage, peak to peak. Again, output voltage will not be DC. It will remain AC, but its peak to peak amplitude, surely it will be less than 10 volts peak to peak, right? So how to find out it, I will just explain you. You just try to do the calculation. Vin 10 volt peak to peak with frequency 10 hertz, C 0.1 microfarad, So first of all, calculate the value of Xc. Xc equals to 1 upon 2 pi into F, that we taken it as a 10 hertz only, into 0.1 micro. How much is the value of Xc?
159 into 10 raised to 3.
Into 10 raised to 3. Means it is 159 almost kilo ohm. Am I right?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay.
159.
So this is the we can say
Yes,
the
sir.
resistance offered by that capacitor. Yes or no? Now say that Xc will not going on to change until we will going on to change the frequency of input signal. Am I right? Because
Yes,
that
sir.
C will remain constant as a 0.1 micro. Whenever I will going on to change the F in, that means the frequency of input signal, then and then Xc will be going to change, otherwise it will remain constant as 159 point something kilo ohm, which you determine just right now. Now we have to find out the VO. Can you determine it? Simply apply the voltage divider rule. See, two resistors shown are connected. It looks like in series, and we are measuring the voltage at the node, which is formed by two resistors. Yes or no? Which you already done in your previous assignment, or I already explained in the previous lectures. Now, in this case, instead of source as a DC, source you have to take peak to peak, that is 10 volt peak to peak into RL, that is nothing but, already I given that value as a 1 kilo ohm. See, this is the node voltage that you have to determine. Can you observe the cursor? We are
Yes,
measuring
sir.
the voltage at
Yes,
this
sir. Yes,
node.
sir. Yes.
With respect to common line, that is nothing but we can say ground. Okay, so how much will be that node voltage? That will be equals to source. Source is now AC, that is 10 volt peak to peak, into the resistance across
Yes,
which
sir.
we are measuring the voltage, that is RL, that is 1K. So 10 volt peak to peak into 1K divided by total resistance of that path. And total resistance is the resistance offered by capacitor, that is 159 point something kilo ohm plus this 1 kilo ohm. So it will be 160 point something kilo ohms. So VO equals,
62 milliampere.
no, it will be in volts. You are
62
determining
volts. Sorry, sir. Volts. Sorry.
62 millivolts, na?
Yes, sir.
Yes, sir.
See, just imagine you are applying this, just try to imagine you are applying 10 volt peak to peak, that means somewhat large amplitude signal as an input, and what you are getting 62, na?
Yes, sir.
Yes, sir.
You are getting
Yes, sir.
62
Yes, sir.
millivolt, 62 millivolt peak to peak signal. Yes or no? And that's why what
Yes,
I
sir.
said, that output will be surely less than that of input. Okay, now if you change the frequency of that input signal from 10 to like 20, 30, 40, 50, etc., or in kilo ohms, the question is what will going on to happen with VO? What do you think?
So increase. It will increase.
VO will increase.
Yes, VO will get increase. Why? Because that denominator total resistance of that path, it will going on to decrease. Is it? Numerator it is fixed. That is nothing but V in into RL. Both are fixed in terms of amplitude. Huh? V in, we are taking the voltage into resistance across which we are doing that measurement. That is RL, which is 1K. So these two terms will remain constant. That means your numerator will remain constant, but at denominator, as denominator is what? Total resistance of that path. That means Xc plus RL. So Xc, that will go on to decrease as you will go on to increase the F in, that means input signal frequency, and hence VO will get increase. As the denominator decrease, VO will get increase as it is inversely proportional. Am I right?
Yes, sir.
Yes, sir.
Okay, now
Yes, sir. Yes, sir.
just imagine there is a graph in front of you. you plotted one x-axis and one is y-axis. You just plotted two axes, one is x and one is y. On x-axis, generally what we are taking the independent parameter, or the parameter which we will going on to change, and accordingly the dependent parameter gets changed or remains constant that we are observing on y-axis. That means with respect to x. So x-axis is independent and y-axis is dependent. Remember this one. So on x-axis take frequency, on y-axis take the output voltage, and start it from origin. How it will look? Initially you will observe, remember, initially you will observe there is linear increase in the output voltage by increasing what? Frequency. Yes or no? Suppose we have plotted, that means there will be one straight line passing through origin like this with somewhat slope. Okay. Remember, at a particular input signal frequency, the reactance offered by that capacitor, it will be as good as, or we can say almost equals to 0 ohm or negligible, and later on it will remain negligible. That means how much will be VO then? A particular frequency, input signal frequency, we will take that frequency, for example 100 kilohertz. Then I will change the input signal frequency from 10 hertz, for example, to 100 kilohertz. Just imagine, at 100k, if I say that Xc is equals to approximately equals to 0. The question is, at 100 kilohertz, how much will be VO? Will it be 0?
Sir, equals to V in.
Yes, correct. Very nice. So that VO will be equals to V in, because your Xc will become 0. 0 means it is not open circuit, it is short circuit. Right? And that's why VO will be equals to V in. Now, as already I told, at 100 kilohertz, if the reactance offered by that capacitor becomes 0, above 100 kilohertz, what will be the effect on Xc? Remember, Xc never goes to, will not be like that. Once it will become almost 0, it will remain 0 later on. That means from that particular frequency, here I taken the example as 100 kilohertz. After 100 kilohertz, the reactance offered by capacitor, it will remain almost 0. It will not go on to goes towards the negative. So it will remain 0, and hence the output will be
Constant equal to V in.
right. So after 100 kilohertz of input signal, the output will be on to follow the input. So this is the graph just in front of you, right? Just imagine. So what you will call this circuit? Is it acting somewhat like any filter?
Yes.
Which filter? Or after diploma students might have already studied all these things in detail about the filters. So see here, we can say it is a high pass filter. For low frequency, generally, for low frequency we are not getting the output, but from a particular high frequency to onward, we are getting the output same as that of input, and that's why such type of filter is known as a high pass. Very simple. Is it? Now we'll switch to the next diagram. So in next diagram, see, instead of connecting that capacitor in series, I place it in parallel. That means capacitor is in parallel with input signal source and the load resistor. Again, if my input signal frequency is 0 hertz, we'll take the same conditions which we discussed when that capacitor was in series. So if input signal frequency is 0 hertz, what will be the output?
Equals to V in.
Equals to V in.
Very nice, because that capacitor will act as open circuit, no current going on to flow through that capacitor. That means the total current will going on to flow through RL only, and hence that output will be maximum. Maximum is nothing but equals to V in. Right. Now the 10 hertz. Okay. If it is 10 hertz, you already determined the Xc offered by this capacitor. That Xc was 159 kilo ohm. That means 159K parallel with 1K. Just determine the equivalent of that 159 parallel with 1K. It will be closer to 1K, and try to find out how much will be the current through that parallel equivalent, and by that current you can determine how much will be the voltage drop. That is nothing but your view. Am I right?
Yes.
Yes,
now,
sir.
now in this case, if I increase the frequency from 10 hertz to onward, like 20, 30, 40, 100, 1K, 10K, etc., what will be going to happen with this XC? That XC will get decreased. At 100 kilohertz, just like previous consideration, at 100 kilohertz, if XC becomes 0, that means this capacitor will be going to provide a short circuit path to the signal source. Yes or no? So the total current will be going to flow through XC only, and no current will be going to flow through the resistive load. That means the voltage across short circuit path is nothing but 0. VO will become 0. Am I right?
Sir.
Again, just imagine a graph is there. First quadrant, plot the x-axis, y-axis. On x-axis, take the frequency. On y-axis, take the output voltage. When that frequency is 0, that is at origin, how much will be the output voltage? Output voltage will be maximum, that is Vin in this case. Right now, up to 100 kilohertz, we can say that output will try to follow the input, and that means not exactly, but here we will consider the ideal case. At 100 kilohertz, if the reactance offered by that capacitor is equals to 0, that means the output will goes to 0, means whatever graph you are observing, just imagine it, this is nothing but what? It is a low pass filter. Are you getting? Because only low frequency signal, or at low frequency signal, we are getting the output. That means that filter circuit passes only low frequency signal towards the output side, while high frequency signal, it gets bypass. Or at high frequency, the signal gets grounded. That means output becomes 0. Is it correct?
Yes, sir.
Yes, sir.
So these two circuits are, one is low pass filter and another one is high pass filter. Is it clear?